Okay, so we need to talk about complex eigenpairs. So we're in the context of trying to solve things of the form uh, y as a vector prime is equal to some matrix A times y. You've probably dealt with a bunch of these by now. If you haven't dealt with a bunch of these by now, please go back, watch the earlier videos, do some homework, come back to me when you're at least a little practiced up on this. My hope is that you've practiced up on this enough to know I know how to at least start this problem, and the way I start this problem is by finding the eigenpairs for the matrix A. So, the trouble that we can have is if we run into a situation where we have a complex eigenvalue, that complex eigenvalue oftentimes comes with a complex eigenvector, and we kind of don't really know what to do with that. My usual is to say, well, the answer looks like y is like c1 times e to the first eigenvalue times t times the associated eigenvector plus c2 times e to the second eigenvalue times t times the second eigenvector, and kind of so on until I run out of eigenpairs. Right, so I'll get to like cn e to the lambda n t xn. We've already run across some like wrinkles in this where we maybe had a mismatched geometric and algebraic multiplicity or something. We've got some tools for dealing with those. But you may have run across a complex eigenvalue by mistake. Either you copied a problem down wrong out of the book, or you solved using quadratic formula and lost a minus sign someplace, ended up with a complex eigenvalue, and that of course gave rise to a complex eigenvector. So we're going to show you how to deal with that. There's a claim that's kind of crucial here, so I'm just going to make this off to the side. So here's a claim. If A has only real entries, so that's my matrix A is made of real numbers, which most of our matrices have been. We haven't talked about matrices with complex numbers in them yet. You may have hypothesized the existence of such a thing, like yes, they exist. No, they're not relevant today. So let's just leave them off. Let's say if our matrix A has only real entries, then the eigenpairs let's see. Let me rephrase that a little bit. Then any eigenpair with complex numbers must have an associated eigenpair made of the complex conjugates. You remember finding complex conjugates. We have run across something very similar to what I'm about to talk through when we ran across complex roots in second order linear constant coefficient homogeneous ODE solving. So when we ran across like R was A plus or minus IB, right? Those were a complex conjugate pair. A plus IB is one of the solutions and A minus IB is the other one. That same thing has to happen with eigenpairs for very good reasons. I'm just going to give you a like really quick sketch of a proof. So let's just suppose that lambda and x is an eigenpair. With complex values. Doesn't really matter where the values are in here. So complex, in order for it to be a complex eigenpair from a real matrix, that's going to mean that lambda has to be complex. That's going to automatically force x to be complex. but that's maybe not necessarily obvious. Let's just suppose that there's complex something or other going on in either one of these. Doesn't really matter for the proof. So once we've supposed that, what that means is that a times x is lambda times x, right? Like that's straight up just what that means. Then I'm going to take a complex conjugate of everything involved with this. So we're going to say a's complex conjugate times, that's supposed to be an x and I drew a lambda, times x complex conjugate should equal lambda's complex conjugate times x's complex conjugate. That's just me taking complex conjugates of both sides of a system. A is real, right? All of its entries are real, so there's no I to swap the sign on, so A is going to give me the same thing when I complex conjugate it. So I'm going to get A, then I'm going to have x's complex conjugate is equal to lambda's complex conjugate times x's complex conjugate. And you'll note this is what it means to be an eigenpair, right? Now we just have a different, possibly different eigenvalue. In practice, it'll always be the eigenvalue that contains some complexity. So I've got my complex eigenvalue that I've now conjugated, and I've got the associated complex eigenvector, which I've also complex conjugated. And that's that. So I know they always come in pairs, which is a little bit important to me. So let's just look at what a solution ought to be. So I'm going to say, let's assume, and I'm going to scroll down a little bit here. So let's assume we have a plus b let me write that the right way. A plus ib and u plus iv. So I've broken both my eigenvalue and my eigenvector into its real and imaginary components. And then because of the thing we just did, that means that a minus ib and u minus iv also has to be an eigenpair. So let's assume we have the one and also the other eigenpairs. Now, because I don't know what the rest of the solution or what the rest of the eigenpairs are, I'm going to be limiting myself to at least part of the solution. So we're going to assume that these are eigenpairs for our matrix A. Then, part of the solution at least, I'm going to write it as C1y1 plus C2y2 should equal C1e to the a plus ib all times t times u plus iv. This is just me plugging this into the same formula that we were using before. This came out of diagonalization, so there's no reason for me to think that complexity matters at all here, right? So this should at least be part of the solution. And I've plugged in both my my kind of first complex pair and my complex conjugate pair, right? So I've got both my pieces plugged in. And then what we ought to do is we ought to be saying, okay, so let's see if we can do the same kind of algebraic rearrangement that we did when we had those complex roots in our spring equations. I would really like to be able to simplify this a little bit and get some real solutions out of it, some like purely real solutions. I don't really want those i's in there. So my hope is that I'm going to be able to fiddle around and then I'm going to be able to absorb those i's into an arbitrary constant someplace along the way. So let's see if we can get that done. So first thing I'm going to do is use an exponent rule to split stuff apart. So I've got C1 e to the at times e to the ibt times u plus iv plus C2 e to the at times e to the minus I bt times u plus iv. Oops, I screwed up. That's supposed to be a complex conjugate, so that needs to be minus iv. Okay, now my next thing I'm going to do is I'm going to use a little bit of factoring. So I'm going to notice that there's e to the at's in common here. So I'm going to write an e to the at out front. Then we're going to make a whole big bracket. We're going to get a C1. I'm going to write this using Euler's, which is going to be cosine bt plus I sine bt times u plus iv plus, out of this guy, I got a C2. I got a Euler's again, cosine of minus bt plus I sine of b minus bt. So I've got a minus sign in there. And that's Euler's, so that's why this isn't a minus sign. That's not me doing a complex conjugate thing. That's literally just me doing Euler's. We'll get a minus sign there in a second, but for a different reason. And then I've got that times u minus iv. Okay, so next thing's next. We're going to have our e to the at chilling out front. And then we're going to do a little bit of multiplying in. So multiplying that in, that's going to be C1 cosine. Oh, whoops. Let's do even odd first before we multiply. Let's go back up here and look at our even and odd. So cosine is an even function. So that minus sign there becomes a plus sign. So that's because cosine is even. Here, that minus sign can migrate out here, and that's because sine is odd. Okay, now we can get to multiplying. So we're going to get a C1, we'll get a cosine bt, and then that's going to be times a u. So I'm going to throw another set of brackets in here for a C1, because that's going to be multiplied by everything here. So I got cosine bt times u. Then I got a plus I sine bt, also times u. Then I got a plus I cosine bt times v. And then I got a minus, because there's an I times an I, so that's going to be an I squared, which is a minus 1. So I got minus sine bt times v plus C2, and then we're going to do a similar thing here. I'm just going to write a quick explanation here. That's from I squared. Okay, so then we're going to distribute again over here. So we've got a cosine bt times u. So cosine bt times u. We got a minus I cosine bt times v. I don't know why I picked a different order to multiply this one out in. Plus, minus, rather. So that minus sign is from this sign is odd minus sign. So I got a minus I sine of bt, and that's going to be multiplied by u. And then I got a minus I sine bt, minus I sine bt. But then there's an I, there's another minus, so that's a plus, v. And I can whack these two i's and make that into minus. So that minus sign is minus I squared. So that's a total of 3 minus signs altogether. Okay. Now we got, that's our closing bracket. That's our big closing bracket. now we're going to go ahead and we're going to collect some like terms. So the like terms I'm going to collect here are going to be the real piece and the imaginary piece. So I got here cosine BTU and here minus sine BTV. So that's the real part in this one. And the real part in this one is cosine BTU and minus sine BTV. So everything in the blue there, these two and these two are the same, right? They're both the real parts. They're both the same. So I should be able to re-add or to add that together as it's C1 plus C2 times cosine BTU minus sine BTV. Then, if I grab the red bits here and here and here and here, you might notice that this one is I times sine BT plus cosine BT. Whoops, I got a U there, I got a V there. Over here, I got a minus I times cosine BTV plus sine BTU. And you might notice those are written in different orders, but those are the same thing here. So I've got an I that I can factor out. If I think about what's actually written there in the red, I got a C1I minus C2I. So I can rephrase that as C1 minus C2 all times I times sine BTU plus cosine BTV. And then I can do that same thing that I did when we were doing springs. I'm going to relabel some arbitrary constants. I'm going to pick this one here, I'm going to call a new C2. And this one here, I'm going to call the new C1. And then I'm going to rewrite this. And this is going to be, I've got a C1, so that's this constant here. I've got a e to the AT, that's from this e to the AT here. And then I got a sine, oops, I got some parentheses. I got a sine of BTU plus cosine of BTV. Then I got a plus, and I got a green C2 here. And I got a cosine of BTU. Oops. Dang it. What did I forget? I forgot my e to the AT. So I got my e to the AT. And then I got parentheses. And then we got cosine of BTU minus sine of BTV. So essentially what this means, right, is that if we want to, instead of using e to our complex eigenvector times our complex eigenvalue plus e to our complex eigenvalues conjugate times our complex eigenvectors conjugate, I can instead use a formula like this. This should feel real familiar. This is that same thing we did before. I'm going to go through a really short example here, but because this video is already kind of long, I'm just going to give you the eigenpairs. So here's my example. Let's say we wanted to solve y is 0, 1, minus 1, 0. Oops, I forgot a y prime. Is y prime equals 0, 1, negative 1, 0 times y. Now, if I want to solve this, I need the eigenpairs. So eigenpairs are I and... Sorry, let me just look at my notes over here. I and the vector minus I1. So that's one of my eigenpairs. Because I know that this is a complex eigenpair, I know what the other one is right away. The other one's minus I and I1. Right, that's just the complex conjugate of the one I just had. So, y should be, well, I need to find my pieces. So, let me think about my lambdas. My lambdas are 0 plus or minus I, right? And I just need to rewrite one of these. So I'm going to rewrite negative I and 1 as it's the vector 0, 1 plus I times the vector 1, oops, not 1, times the vector negative 1, 0. So then if I want to use my solution here, I can say, okay, so y is equal to, this means that a is 0 and b is 1. And then that piece is u, and we're talking about u plus iv there. So I can just use my formula. So I can say, okay, so y is c1, and in this case, I said that this was part of the formula, right? I don't have any extra eigenvalue, or there are no more eigenpairs for this. I already found them all. So I can just use these two, and it's the whole solution. If I had a 3x3 matrix, I might have a case where I have a complex conjugate pair for 2 of the eigenvalues, and then a real one for the other one. Note, you can't have 3 complex eigenvalues for a problem because they have to come in complex conjugate pairs. Okay, so y is c1 times e to the 0t times sine of t times my vector u, which is 0, 1, plus cosine t times my vector v, which is minus 1, 0, plus c2 times e to the 0t times cosine of t times my vector u is 0, 1. Oops, that needed to be a minus sign. Minus sine of t times my vector negative 1, 0. And that's my answer there. We could simplify that just a touch. Right? These things are 1. They don't need to be there. We could do some vector multiplication to kind of collapse things a little bit if we wanted to. That would be an option. But I'm happy with you turning in this as an answer. Thanks for watching. I will catch you on the next one. I just realized that I have these... I have my C1 and C2. I thought I was doing something clever, and I swapped them from the back of from Will Trench's book. So these solutions would be y2 is this one in Will Trench's book, and y1 is this one. Let me grab that and show it to you. So here's the theorem I'm looking at. So I didn't really claim which of these is y1 and y2, but I kind of implicitly did it by labeling my c1 and c2. You'll notice that he's got this one, right? Cosine bt u cosine bt minus v sine. So he's just got them backwards from what I have. Same. Don't sweat it. The order of the solutions doesn't matter. If you have more more eigenvalues. You just need to add those using either. So if you have more eigenpairs, you can just add them using either this technique again for a complex conjugate pair, or you can do the thing that we've been doing in sections past where you just do c e to the lambda t x. Or if you have repeated eigenvalues that have a lower algebraic multiplicity, you might combine this. I'm not, as an instructor, going to ask on an exam for you to do anything bigger than a 3x3 matrix. So I couldn't ask one of those combo questions. But if you ran across a 10x10 matrix out in the world, you might have to apply all three of these techniques in the same problem, and you could just do that. It's fine. The superposition principle still applies. You can still just add them together. All right. And on that note, thank you. I will catch you guys on the next one.